Okay, welcome to this video on mechanical properties, part one. Let's start by thinking about simple experiences that we may have had where we may have interacted with a spring. And so what you may have learned from other courses or your everyday life is that the extension of the spring, here plotted on the y-axis, is proportional to the force applied to that spring. And so Hooke's law tells us that proportionality correlation goes with a linear format. So that is, the extension x is linearly proportional to the force applied with the proportionality constant here called the spring constant, K. Okay, so in other words, if you were to apply force F to that spring, you would expect extension X, and applying twofold F, you would get double the extension with a total there that is correlated and governed here by the spring constant K. Okay, so that's Hooke's law, and an assumption here is that this is valid for a reversible and linear response, kind of limits, if you want, to the spring. If those of you who have interacted with metal slinkies, for example, you know if you overextend them, the forces applied and the extension applied to that slinky have led to permanent deformation of the spring, and you've exceeded the limits of Hooke's law in that analogy. Okay, so these ideas we're going to build on as we establish mechanical properties and tensile test work as an example for our course here. Okay, some other things that drop out of Hooke's law. The area under this curve we've plotted here for the extension of the spring versus the force applied to extend that spring. The area under the curve here represents the following. So that would be a force times distance would give the appropriate area under the curve. Okay, and so force times distance, some of you may know, is equivalent to work, and the units for work are in joules. So it follows that force uses newtons for those joules. Distance might be measured in meters. And so we have here that a newton times a meter is a joule. Okay, so that's something we also have out of this. And we'll see in later stress-strain curves that the area under the stress-strain curve is going to also have some implications for a property of the matter in question. Okay, so building off of that, the next thought here is to consider all matter as having properties of a spring, meaning that it can extend and in a reversible fashion and have a linear correlation between the extension length and the force applied. Okay, so that's one new thought for us. What we have now with with real matter rather than a spring is that we have some structure to it. We have a size and shape to it. So to help us kind of normalize the property, to make it not the characteristics of the extension versus force applied, to normalize that, we need to know the cross-sectional area that is orthogonal to the force applied to the object. Okay, so imagine that our spring is now an arbitrary box of matter, and we will be applying the force to it as we did in the previous slides here. We see here that the force applied here extends through the length of our purple box, and there's a cross-sectional area represented here by the green plane. So that is the orthogonal cross-sectional area to the tensile vector, that is, by applying a tensile force from one opposite end of our rectangle to the other. Okay. So to transform force into something that can normalize for the cross-sectional area, we define here stress. So tensile stress, because we are pulling in tension on the object, tensile stress is going to be the force divided through by that cross-sectional area. Okay, so that gives us the tensile stress for the measurement now. Because this is still a tensile experiment, we're still pulling on the object. We now extend our thoughts here on simply the length of the spring, but now redefine that as strain. Okay, so here we see that we've defined stress, force normalized for the cross-sectional area, and the strain now is going to be a unitless metric, and it's going to represent the change in length divided by the original length when there was no force applied. So clearly there was some length to this rectangle, this rectangular box, and so that might be L naught was the original length, and the change in length would represent, say, 2x here in our previous experiment, or we might now call that delta L, the change in length. So we're going to define tensile strain, and we will be using epsilon for that, will be the delta L divided by the original length, L naught. This is how we end up with a unitless parameter that is our strain value. Okay, so these are some new ideas. We'll see that most of the data follows similar to Hooke's law, and that we'll have a linear correlation between the quote-unquote force versus the extension, or rather, better said now, as the stress versus the strain. Okay, so in the previous slide, we didn't talk about this, and we can give some attention to this now. So we know that in the previous slide, if we overextend a spring, we will kind of exceed the reversible loading of that spring, and some permanent deformation will occur. And so the same thing can be said for matter. If we overextend matter, we will register some permanent deformation on it. And many of you have witnessed this if you overbend your plastic pencil or pen or something, that you will put some permanent deformation to it. Okay, so some takeaways here. We saw in the analysis for Hooke's law that we had a proportionality constant. This was the spring constant, and it could be calculated as simply the slope of the force versus extension length curve from the spring. So in other words, it would be force divided by x in that case, and that would calculate our spring constant, the slope of that graph. We're going to see here, as in the following slides, that we're going to define an analogous equation here to that of a spring, where we're going to, instead of having a proportionality spring constant, we're going to define Young's modulus, which has similarities to that of the spring constant. It characterizes the linear portion of our graph. Because we were in newtons per meter squared on our stress sigma versus strain curve, our slope here is going to be the units of the y, which could be megapascals or pascals, divided through by a unitless x-axis, because of course it's rise over run, and rise is the y dimension, and run is of course the x dimension. And so our units for the Young's modulus are going to be the same as our y-axis, only because our x-axis is unitless, per our strain being defined as delta L, length under loading minus the original load divided through by that original length, L naught. Length under load minus original length divided by original length. Or, as we said a moment ago, delta L over L naught. Okay,